When we proved the power rule, the derivative rule for power functions, we really only did it for positive integer powers here, although we said you could use it for any power. Uh, with the quotient rule, I can now at least prove it for the negative integers. So, for instance, the power rule is telling me that the derivative here should be negative 3x to the negative 4, right? So, yeah, you bring the exponent down and then you subtract 1 from the exponent. Well, let's actually do this with the quotient rule. That is, I'm going to rewrite this function as 1 over x cubed. And then I can see this as a quotient. So y prime is, I've got the x cubed squared on the bottom. I've got the x cubed times the derivative of the top minus the top times the derivative of the bottom. Well, I'm going to use the power rule here to take the derivative of the bottom, but now it's a positive integer power, and I already have proven that this works for positive integer power. So what do I have here? I've got x cubed times the derivative of 1. Oh, derivative of 1 is 0. Minus 1 times the derivative of x cubed. Well, that's 2x squared. Actually, it's 3x squared. And then that's an x to the 6th on the bottom. So what I have is, I've got a negative 3x squared over x to the 6th, which looks like a negative 3 over x to the 4th, which I could write as negative 3x to the negative 4, which I think is what I was expecting. Yes, it is what I was expecting. Okay, so there it is for a particular value. I can do it in general now. In general, if n is a negative integer, then I'm going to look at y equals x to the n, which I'm going to rewrite as 1 over x to the negative n. Now remember, if n is negative, then negative n is actually positive. So using the quotient rule to get y prime, I have x to the negative n squared. I have x to the negative n times the derivative of the top. That's going to be a 0. Minus the top times the derivative of the bottom. So here we go. The derivative of 1 is going to be 0. So the numerator here is just, there's that negative 1, and then there's the derivative of x to the negative n. Remember, negative n is positive because n was negative. It's like here n was negative 3, so negative n was positive 3. So here we go. I've got, so that was a 0, and then a minus 1 times, this is negative n x to the negative n minus 1, where n is a positive number, so this works. And then I've got x to the negative 2n here. For a grand total of, it looks like the negative 1 times negative n is n. I've got x to the, I'm going to make this a negative, well, no, I'll just leave it that way. Negative n, negative 1 over x to the negative 2n. So this would be equal to n x to the, I'm going to be a little careful here, make sure I get all my signs right. This I'm going to bring up to the top as x to the positive 2n. And so what I have is n x to the, add the exponents. I have a 2n minus n, that's n, and then I have a minus 1. And there we go. The derivative is nx to the n minus 1. Okay. So in general, I don't do that. If I'm looking at a function like this, if I say y equals 1 over x to the 4th power, I would not take the derivative by the quotient rule. You could, it'll work, but easier is to say x to the negative 4 and just use the power rule. Y prime is negative 4, x to the negative 5. Okay. But because of the quotient rule and the power rule for positive integers, we now know that this is actually true for negative integers as well.